Hi class. In this video I'm going to go over stoichiometric relationships with gases. We'll go over density in the ideal gas law, molarity in the ideal gas law, and also gas mixtures. Now I know in, I don't know if it was my Tuesday, Thursday class or Monday, Wednesday class, we already went over density and the ideal gas law, molarity and the ideal gas law. So if you understand that, then you can just go ahead and skip it. So let's take a look at this problem here. And in this problem, we're asked what volume of hydrogen and nitrogen gas is required to synthesize 250 liters of ammonia at standard temperature and pressure. So, obviously, you could use the ideal gas law. We have a balanced chemical equation. But if we look at the equation, everything in this equation is a gas. Okay? So remember, the pressure is equal to nRT divided by V. So the pressure is directly proportional to the concentration, okay, in moles per liter. This N over V is concentration. So what we can do, as long as all of the substances in the chemical reaction are gases, what we can do is we can relate the pressure to the volume. Okay, so here we're asked, we're gonna produce 250 milliliters of ammonia, and again, that's standard temperature and pressure. That's 1 atmosphere and 273 Kelvin. So all I need to do, wait a minute, let me write the ammonia in here. All I need to do is use the stoichiometric coefficients from the chemical equation. So we have 2 moles of ammonia for every, let's do hydrogen, 3 moles. Oops, I'm sorry. I'm reading from the equation. So what we can say is that we have 2 liters of ammonia for every 3 liters of hydrogen gas. So this would be 250 times 3 divided by 2. And that would be 375 liters of hydrogen. And then we can do the same for the nitrogen. We have 250 liters of ammonia, and we have 2 liters of ammonia will produce 1 liter of nitrogen. We just use this equation stoichiometry. So that would be 250 divided by 2. That would be 125 liters of nitrogen. Again, you can do this when you have all gases in the chemical equation and you're asked for the volume. Okay. Here's a problem here. We're asked to design an airbag for a car. We know that the bag should be filled with gas and that has a pressure higher than atmospheric pressure, so 835 millimeters of mercury. I even converted that to atmospheres at a temperature of 295 Kelvin. So the bag has a volume of 54.6 liters. What quantity in grams of sodium azide should be used to generate the required quantity of gas? So what we need to do is use the ideal gas law, and we're given the pressure of the gas. The gas is nitrogen. we're given the temperature, and we're also given the volume. So what we need to do is solve this for the number of moles. So the number of moles is going to be pressure times volume divided by RT. So let's find the number of moles. Let's see, the pressure is 1.097 atmospheres, and then the volume is 54.6 liters. And we'll divide that by R, which is 0.0821 liters atmospheres per mole Kelvin, times the temperature, which is 295 Kelvin. So let me put this into the calculator. We have 1.097 times 54.6, and we'll divide that by 0.0821 times 295. And so we end up with 2.47 moles. So this would be 2.47 moles. So now it's just a matter of using the balanced chemical equation to find the number of grams of the sodium azide to use in order to generate this much gas. So we have 2.47 moles of nitrogen, and according to our balanced chemical equation, we have 3 moles of nitrogen for 2 moles of the sodium azide. So there we go. And then we just need the molar mass of the solid. So let me see here. We have, where's my periodic table? Grab a periodic table here. And sodium is 22.99. 22.99 plus 3 times the molar mass of nitrogen, which is 14.0067. And so the molar mass is 65. 22.99 plus 3 times, okay, 65.01 grams per mole. So 65.01 grams per mole. Then we just put this in the calculator, 2.47 times 2 divided by 3 times 65.01. And we would need 107 grams of the solid. Okay, so these are just like the problems we were doing before. It's just that, you know, sometimes we need to use the ideal gas law. So let's talk about the ideal gas law and gas density. And it turns out the density of a gas is directly proportional to its molar mass, and it's inversely proportional to its temperature. Okay, so we have our ideal gas law, PV equals nRT, and N, the number of moles, is equal to the mass divided by the molar mass. So we're going to go ahead and substitute this in here for N. So pressure times volume is equal to the mass over the molar mass times RT. So what we remember, density is mass over volume. So I'm going to bring the volume over here. So pressure is going to be equal to the mass times R times T divided by the volume times the molar mass. So here, this is density. So the pressure is equal to the density times R times T divided by the molar mass. And then we can just solve this for density. So the density is going to be equal to the molar mass times the pressure divided by RT. So if you know how to derive these equations, it's great because it's not something else you need to memorize. So here we're asked, what is the density of argon gas at standard temperature and pressure? So what we need is the molar mass of argon. So argon has a molar mass of, let me look it up on the period, 39.948. 39.948, that's grams per mole. And then it's STP, standard temperature and pressure, so we have a pressure of 1 atmosphere. We'll divide this by R. Let me move this up for a minute. And that's 0.0821 liters atmospheres per the quantity moles Kelvin. And then times the temperature, that'd be 273 Kelvin. So we see that everything here cancels out, except we're left in grams per liter, which will be the density in grams per liter. So 39.948, and then we'll divide that by 0.0821 times 273, and I get a density equal to, whoops, okay, why is it doing 1.78 grams per liter. Next, we'll take a look at the molar mass from the ideal gas law. And again, we start with, the ideal gas law. PV is equal to nRT. And of course, N is the molar mass, is the mass of the substance divided by its molar mass. So we substitute that in for N. And then we just go ahead and solve for molar mass, and we end up with this equation here. It's equal to the mass times R times the temperature divided by the quantity pressure times volume. So here we're asked, what is the molar mass of 1.10 grams of gas that occupies 0.56 liters at standard temperature and pressure? So we'll go ahead and use this equation. The molar mass is equal to the mass, which is 1.10 grams, times R, which is 0.0821 liters atmospheres per mole Kelvin. And that would be divided by 1 atmosphere of pressure, we're at standard temperature and pressure, times the volume, which is 0.560 liters. So we see here that everything, we're missing our temperature. That's 273 Kelvin. I was going to say that should be canceling. See, that's why it's a good idea to use your units. Always include your units. So now I'm left in grams per mole. That'll give me the molar mass. So 1.1 times 0.0821 times 273 divided by 0.56. And I get a molar mass of 44.0 grams per mole. So again, if you can derive these equations, they're less to memorize. But that's up to you how you do that. Okay, let's take a look at gas mixtures. Okay, that means, think about air. It's a mixture of gases, oxygen, nitrogen, argon, and so on. But anyway, we already talked about how gases will mix homogeneously in any proportions to form a solution. So each gas in the mixture would behave as if it's the only gas present, because remember, gas particles are so far apart that they don't influence each other. So basically, we define the partial pressure as the pressure exerted by each gas in the mixture. So we follow Dalton's law for this, and Dalton's law states that the total pressure of a mixture is the sum of the partial pressures of the gases in that mixture. So the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2, and so on. So it turns out that the partial pressure of a gas is proportional to its mole fraction. And mole fraction, excuse me, is represented like so. So what is the mole fraction? So a mole fraction, so you have a mixture, and we have 2 or more substances in that mixture, and the mole fraction of, let's say, component A of that mixture is going to be equal to the number of moles of A divided by the total number of moles of that mixture. Okay, so for example, if we have a mixture of, let's say we have, 3 moles of nitrogen and 1 mole of oxygen. And if I were to ask you, well, what is the mole fraction of the nitrogen, it would be, we have 3 moles of the nitrogen, and then we have 3 plus 1, we have 4 moles in the mixture. So that'd be 3 divided by 4, which would be 0.75. Now, one thing you need to know is that the sum of mole fractions in a mixture is equal to 1. So if I wanted to find the mole fraction of oxygen, I could do it one of 2 ways. I could do it the same way as I found the nitrogen. It'd be 1 divided by the total number of moles, 1/4, right? So it'd be 0.25. Or, since there are only 2 components in our mixture, I can just subtract the 0.75 from 1, and I get 0.25. So the sum of the mole fractions, again, has got to be equal to 1. Notice mole fractions do not have units, and that's because they cancel out. Okay, so let's take a look at this problem here. Oh dear, let me just get out of here and go back in. Okay, so let's try this problem here. We have acetylene reacts with oxygen to give carbon dioxide and water vapor. So we have this balanced chemical equation here. If we mix acetylene and oxygen in the correct stoichiometric ratio, in other words, 2 moles of acetylene with 5 moles of oxygen, and if the total pressure of the mixture is 140 millimeters of mercury, what are the partial pressures of the gases before the reaction occurs? Now remember, back here, a partial pressure is equal to the mole fraction times the total pressure. Okay, so let me go ahead and write that down. So the partial pressure of acetylene is going to be equal to the mole fraction of acetylene times the total pressure. And the mole fraction or the partial pressure of the oxygen is going to be equal to the mole fraction of the oxygen times the total pressure. Okay, so we need to find the mole fraction of the acetylene, so that's C2H2, and that's going to be equal to the number of moles of acetylene. So we have 2 moles because we're calculating this before the reaction takes place. So we have 2 moles of acetylene, and so I'll put 2 moles here, and then we need the total number of moles. We have 2 moles of acetylene and 5 moles of oxygen, so that'd be 2 moles divided by 7 moles. So that'd be 2 divided by 7. That'd be 0.29 as a mole fraction. And then the mole fraction of the oxygen, that's going to be equal to 5 moles of oxygen divided by the total number of moles. That's 7 moles total. Let me put the moles in here. So 5 divided by 7, that's 0.71. So 0.71. So now we'll find the partial pressure of each gas. For the acetylene, we have the mole fraction, which is 0.29, times the total pressure, 140 millimeters of mercury, and that would be 0.29 times 140, and that'd be 40 point, or I'll just make it 40 millimeters of mercury. And again, I could do the same thing for the oxygen as well, but I already have the total pressure, and here I have the partial pressure of the acetylene, so the partial pressure of the oxygen would be 140 millimeters of mercury minus 40. Okay, so we'll just go ahead and write this out anyway. So this would be 0.71 times 140 millimeters of mercury, and 0.71 times 140 is 100 millimeters of mercury. Again, I could have just taken the 140 minus the 40 millimeters of mercury, and I would have gotten 100 millimeters of mercury. So partial pressure that's really important. Let me exit out of here again. There, that fixed that. Okay, another problem I'd like to do is one that includes collection of gas over water. So I think you've done one of these in the lab. So basically, we have a gaseous product that is insoluble in water, and it's bubbled through water, and then it's collected in another vessel. So basically, what we do is we go ahead, after all of the gas is collected, then what we do is we move the flask up and down until both water levels are equal, and so the total pressure is going to be equal to the atmospheric pressure. But the thing is, the pressure of that gas, that's the total pressure of the gas. That includes the gas and the water vapor. Okay, so what we need to do is we need to subtract from the total pressure the pressure of the water vapor at the temperature of interest. So this is a table that has vapor pressures of water at different temperatures, and there are even more extensive tables that you can get. So for example, here in this problem, we have zinc reacting with dilute hydrochloric acid to form hydrogen gas. And in order to do this, we collect the gas over water at 16 degrees Celsius. So the total pressure, okay, once we adjust everything, is 0.989 atmospheres. So that includes the pressure of the hydrogen plus the pressure of the water. And the volume here is 1,495 milliliters. We want the partial pressure and the mass of hydrogen to be calculated. So basically what we need to do is, we're doing this experiment at 16 degrees Celsius, so we need to look up the vapor pressure of water at 16 degrees Celsius, and it's 13.6 torr. So 13.6 torr. So 13.6 torr. In order to subtract this from the 0.989 atmospheres, we'll need to convert this to atmospheres. So 760 torr is 1 atmosphere. So 13.6 divided by 760. And that's 0.0179 atmospheres. So now we can do that subtraction. So we have 0.989 atmospheres minus 0.0179 atmospheres. So 0.989 minus 0.0179, and that is 0.971, 0.971 atmospheres. So this is the partial pressure of the hydrogen, and so we've calculated that, but now they also want the mass of the hydrogen. So what we can do is use PV equals nRT. Solve this for N. That's going to be PV over RT. So the pressure is 0.971 atmospheres times the volume, which is 1,495. Oh, that's in milliliters. We need that in liters. So we divide this by 1,000, so that's 1.495 liters, divided by R, which is 0.0821 liters atmospheres per mole Kelvin, times the temperature, that's 16 degrees Celsius. We have to convert that to Kelvin. So 16 plus 273, that's 289 Kelvin. 89 Kelvin. And we see that temperature cancels, atmospheres cancels, liters cancels. So we're going to end up with moles. So 0.971 times 1.495. Whoops. Yeah. Oh no, I just cleared it. Okay, 0.971 times 1.495. And that'd be divided by 0.0821 times 289. Oh no, what is this? And I get 0.0612 moles of gas. And we just convert this then to grams. So 0.0612 moles of hydrogen, and diatomic hydrogen is 1.4 times 2 it has a molar mass of 2.02, so 2.02 grams per mole. So that's 0.0612 times 2.02. And I get 0.124 grams of hydrogen would be needed. Okay, so as far as the exam goes, anything up to this point could be on the exam from the gas law chapter. So, you know, everything that we've covered from the stoichiometry, the gas laws, pressure, everything up to or through collection of gases over water. So make sure when you're watching this, go ahead and take notes and jot down any questions you have. And if you're in my Monday, Wednesday, Friday class, ask me on Monday. If you're in my Tuesday, Thursday class, then ask me on Tuesday. So everybody have a great rest of the day, and I'll see you this coming week. Bye-bye.